Hello everybody. Today we're going to do some problems with molarity, percent by volume, and both freezing point depression and boiling point elevation. So first, molarity. Here's the general equation where molarity, which is a unit of concentration, is moles of dissolved solute divided by liters of solution, or sometimes solvent. You'll see those are very similar. So let's take a look at problem 1. Calculate the molarity of a solution with 89.8 liters of solvent and 5.55 moles of solute. Well, this one's pretty straightforward. Let's just plug in what we see. And plug that into your calculator and get 0.062 molar. There you go. Question 2. Calculate the amount of solvent. We're looking for this. In a 1.45 molar solution, we know the molarity. With 18 moles of solute in it, we know the solute. So now we want to solve for x, and what we're going to do is multiply by x on both sides, and then divide by 1.45 on both sides. And simplify 12.4, and since we're solving for amount of solvent, the unit is liters. Calculate the number of moles of solute in a 1.33 molar, so we want moles of solute, we have molarity, we have liters. To solve this problem, we're going to multiply by 4.4 on both sides. And we get, in this case, moles. With these three problems, we have solved for every variable possible in a molarity problem. Let's use this to review. Now let's take a look at 4. For these series of problems, we're going to use percent by volume, which is simply liters of solute divided by liters of solution. Sometimes you'll see liters of solvent times 100. In this question, we're looking for the percent. And we have our solute, which is alcohol, and 7.77 liters of total solution times 100 to make our answer come out as a percent, and we get 85.7% alcohol solution. Question 5, juice. What is the volume of juice, volume of solute? If we have a 4.5 juice solution, we know the percent, and the volume of the total is 12.2. So first things first, I'm going to get rid of this 100 in order to make this percent into a decimal. To solve this, I'm going to multiply both sides by 12.2. And when I plug that into my calculator, I get 0.55 liters. So there are 0.55 liters of juice in a 4.5 juice solution with a volume of 12.2 liters. Next problem. Here we're going to solve for the volume of the total solution, knowing the solute and the percent. And since we know we're going to have to get rid of this 100 anyway, I'm just going to start the problem by writing 29% as a decimal. From here, we're going to do something similar to what we did in question 2. We're going to multiply by x and divide by 0.29. This gets us 9.55 liters of total solution. For question 5 and moving forward, we're going to be using this equation here, where the change in temperature is K, a constant for every different substance, times molarity. And this delta T is going to tell us how much the boiling point of a solution rises above the pure solvent, or the freezing point falls below the pure solvent's freezing point. This is called freezing point depression and boiling point elevation. Since freezing points go down, our number delta T should be negative, and so we can have K be negative, since we can't have a negative concentration. Since boiling points go up, K should be positive, so that the change in temperature is positive. Let's see how our problem plays out. What is the change in temperature? If K is negative 5, there are 5 moles of solute, and molarity is moles of dissolved solute divided by kilograms of solution, and they're at 3 kilograms. Simplifying this, we get negative 25 over 3, which further simplifies to negative 8.3. The degrees here can be Celsius. They can also be Kelvin. Celsius and Kelvin have the same magnitude. They're the same size temperature scales. They're just offset by where the 0 is. So you can put whatever you'd like here. Okay. Number 8. Solution depresses its freezing point by 10. That means its freezing point went down, so we're going to put it as negative. And the K is negative 7. Oop. Forgive me there. Negative 7. We want to know how many moles of solute there are, and it's each kilogram of solvent, so each is just 1. X over 1 is just x, and we need to get rid of this negative 7, so we're going to divide it on both sides, which gives us this. Putting that into your calculator, you get 1.4 moles. Remember, in problems like this, you can't have negative moles. This number should always be positive, so remember your negative signs. Question 9. Solution depresses its freezing point by minus 5. Well, they already included the minus for us there. Thank you. And there are 3 moles of solute in every 2 kilograms of solvent. What's K? Well, what I'm going to do is multiply by 2 on both sides, and then divide by 3 on both sides, which will simplify to this. Which is then, and finally, K being negative is allowable because we're talking about freezing point. And the change in temperature was negative, and that negative has to come from somewhere. It comes from K. Number 10. Here we're talking about boiling point. When we're talking about boiling point, which increases, K will be positive. Simplifying this, we get 1/3 times 3, which is 1 degree Celsius, Kelvin, whatever you'd like, but ultimately the boiling point increased by 1. Number 11. Here, elevation of the boiling point is 9 degrees Celsius. K is 3. We want to know how many moles, and there's 10 kilograms of solvent. I'm going to multiply by 10 on both sides, and then divide by 3. X equals 30, and in this case it's 30 moles that we solve for. Finally 12. Boiling point goes up by 6. There are 2.5 moles of solute in 1 kilogram of solvent. What's K? Well, 2.5 over 1 is just 2.5. And since we want to get K isolated, we're going to divide by 2.5 on both sides. Here, K should be positive because we're talking about boiling point, and boiling point increases. Hopefully this helped. Any problems you might have with molarity, percent by volume, or change in temperature. Thank you. Have a nice day.